The discovery of X-rays was made in 1895 when German named Wilhelm Röntgen was conducting a number of experiments on cathode rays, emanation of electrons from the cathode end of a vacuum-pumped glass tube. Cathode rays are invisible, but Röntgen observed their existence from the fluorescence effect they produced when a screen coated with barium platinum was placed close to the window. He then repeated the experiment but without aluminum windows and discovered that this time the screen flushed, even when it was several meters away. Clearly, this was not the result of cathode rays but a new form of radiation. Röntgen named his discovery X-rays and found that the relative transparency of objects was dependent on their density. With this discovery, the stage was set for the creation of the modern science of X-ray crystallography. Let's talk about SAXS. The small angle scattering of X-rays was one of the further development of the theory of the diffraction of X-rays. The first observation was made in 1937 by Guinier. First application dates back to the late 1930s, when the main principles of SAXS were developed in the fundamental work of Guinier following his studies of metallic alloys. In the first monograph on SAXS by Guinier and Fournant, it was already demonstrated that the method yields not only information on the sizes and shapes of particles, but also on the internal structures of disordered and partially ordered systems. In the 1960s, the method became increasingly important in the study of biological macromolecules in solution, as it allowed one to get low-resolution structural information on the overall shape and internal structure in the absence of crystals. A breakthrough in SAXS came in the 1970s. Thanks to the availability of synchrotron radiation and neutron source, they later paving the way for contrast variation by solvent exchange of H2O for D2O and specific deuteration methods. It was realized that scattering studies on solution provide, at a minimum, investment of time and effort, useful insights into the structure of non-crystalline biochemical systems. Moreover, SAXS also made possible real-time investigation of intermolecule interactions, including assembly and large-scale conformational changes in macromolecule assemblies. In the 1980s, progress in other structure methods led to a decline of the interest of biochemists in SAXS studies, which draw structural conclusions from just a couple of overall parameters or were based on trial and error models. The 1990s brought a breakthrough in SAXS data analysis methods, which opened the way for reliable ab initio modeling of macromolecule complexes, including detailed determination of shape and domain structure and the application of rigid body refinement techniques. This progress was accompanied by further advance in instrumentation, allowing sub-millisecond time resolutions to be achieved on third-generation SR source in the study of protein and nucleic acid foldings. In 2005, a 4-year project was started, Small Angle X-ray Scattering Initiative for Europe, SAXIER, with the goal to combine SAXS methods with other analytic techniques and create automated software to rapidly analyze large quantities of data. The project created an unfunded European SAXS infrastructure, using the most advanced methods available.